In this video, we're going to go over some of the basics of using a digital volt ohm meter like this. We often call it a DVOM or a DMM, a digital multimeter. But we're going to take a close look at this BluePoint snap-on base product. This is the one that we use here at Parkland College. We're going to cover some of the basics of tool setup, lead placement, checking the fuse integrity in the back, so knowing that I've got a good tool to start with. And then we'll go through some of the basic testing using this S.E.T board to look at voltage and volt drops, look at resistance, and also look at current measurements. So we'll start with this multimeter. This is a BluePoint product, so a snap-on base product. This is the common meter that we use here at Parkland, and pretty basic to set up. And the great thing about multimeters is that they're rather consistent. So there's a lot of similarities in how these get set up and how their operation is carried out. So on the dial here, this is kind of my main starting point. I've got off and I've got different modes. And so all the modes that we're going to talk about in class and different theories of where to apply these things. We've got voltage, both in DC and AC. I've got millivolts that can flip between both AC and DC. I've got resistance, as well as some other continuity and diode checks. I've got then 3 very small range amperage measurements, and then I've got my standard amperage or current measurement here. And for each of these cases, they show you the different AC and DC applications. And then those symbols that are up here also correspond with the bottom. So if we take our leads out of the bottom here and look closely at my choices, you can see I've got my volt, ohm, and diode checks all function from that red port. I've got my COM port, which is essentially my ground. There's a ground symbol there in the center. And that's the relative or comparative point for all the modes in red. So if I can match some colors, anytime I do a measurement, I've got a red lead that's going to go in one of these 3 ports, whether that's voltage or some of my currents. And then I've got my black lead. That's going to be my other lead that will always live in the COM port. Meters will typically give me my fused rating down here. And so I can see that in my first port with milliamps, I've got a max of 500 milliamps. So I've got half an amp worth of coverage there. Anything above that, and I'm going to pop the fuse that's inside. And then on my regular amperage, I've got 10 amps. One of the things that I've got to pay attention to with my meter is making sure that I've got good equipment. So let's start with some of the ways that I could go through to audit this and make sure that everything's going to work okay. One of the early challenges with electrical testing for a lot of my students is that it's not the most tangible thing. And so there's often a lot of uncertainty in whether or not you're doing this properly. So one of the things we can do is start by going to resistance and the omega symbol there in the center. When I first hook up, I should get an out of limit OL reading. If I take my leads and I touch them together, as long as I have a good set of leads with good connections at the meter, I should see pretty close to 0. So see there, it tipped just to 0.1, but really we're at 0 ohms. And so that's telling me that this meter's got the ability to make a connection between these 2 points down here, and that my leads also, their integrity is in good shape. The other way that I can check this, I could push this button here that's got the audible symbol and the diode. If I push that once, I get it up here in the corner, and now when I touch these, I get a solid beep anytime that there's continuity. And so that's a quick way again. Now I feel pretty good that my leads are hooked up. They have the ability to measure things that I touch at these 2 points. The other setup that I want to look at and pay attention to, depending on what I'm going to use this meter for, is the integrity of the internal fuses, this 10 amp and 500 milliamp or half amp fuse. And so one of the ways that I can check that on this particular meter is to go to the omega ohm testing symbol, and then I'm going to enter the diode test function. So I push the button here with the diode symbol and continuity check twice until I get the diode in the upper right corner of the screen there. Once that's up there, I can take my lead. I've got it placed in the volt ohm port diode check right here, and then I take it, I go to the milliamp port, insert my lead. As long as I get a change on the screen, so as long as I go from OL to some number, that fuse is good. I repeat that, I go on the amp side. Here, it reads 0, but again, it's a change that I'm looking for. And so with this particular meter, both those fuses are good. So here I've got another meter. We're going to go through that same process to check the fuse. I'm going to go enter the diode mode, take my red lead, go here in the milliamp port. I get a change. That's a good fuse. In my amp port, no change. So this is an example of a bad fuse. And so the method for fixing that on this particular type of multimeter is that we've got to remove our protective cover, take this back cover off, and then there are 2 fuses for 0.5 amp and 10 amp that exist behind that cover. So here's underneath that cover, I've got my 2 glass fuses. We found our 10 amp fuse to be bad, so we're going to pull that one out and put a new one in. I've got my set of new 10 amp fuses. With that fuse out, we can see really clearly that this fuse has got a break in it. And so we will talk about, as we go through current measurements, how to avoid making this happen. With a new fuse, we'll go back through, repeat our check. Now we show that we've got a good fuse. So that's one way that we can check fuses, but it is unique to this meter. And so depending on the kind of meter that you're using, you'd have to read the instruction manual to see if they've got that sort of internal check built in for auditing the fuses. One thing that you can do that is universal is take your meter, regardless of how it's built, and basically use some kind of light source. Typically, most technicians, we've got a test light pretty handy like this. And so we could use this 12-volt test light to basically perform the same sort of check. And so if I use my A-Tech board here as my 12-volt source, when I'm plugged into the 12-volt source, I see my test light works. And so I can check this really fast just on the battery underneath the hood. Come to my meter. We're going to go just to the amp port here, put one of my leads on my test light probe, put the other one to my 12-volt source, and here I get a light and a reading. This is a quick universal way that I can check any meter to decide does it work, because I've got my test light. I have a quick, easy ability to prove that that works. I know my bulb works. I know I have 12 volts, and then bring my meter into it in a pretty controlled way and say, look, that meter works. And so then I can look at, based on starting out with the larger fuse, I've only got about 0.1 amps. So I know that it's safe to switch over to my milliamp source, repeat the same test, and here it works. So nice universal way. I can do that with any kind of meter, regardless of who built it. So the first thing we're going to cover with our DVOM is how to utilize this to do resistance checks. Checking resistance in something is pretty straightforward, and I think it's one of the great ways to begin going through meter usage. So to measure ohms, I'm going to start by going to my omega symbol on here. This represents ohms, which is my unit of measurement for resistance. I make that selection. I should see OL up here initially. This particular meter is going to auto range and it's going to go through the different units of ohms, whether that be mega ohms, kilo ohms. Okay. Down here at the bottom, just complete my setup with my leads. I need my red lead in the volt and ohm port. I see again that omega symbol there. And then my COM port is going to be my other point. Once I got that set up, I'm going to go ahead and set it here. And we'll look at some of the things that I've got on the A-Tech board. And so using resistance is a great way to check things like continuity or check specifications for resistance, because we know that resistance is going to play a big role in current flow and volt drops because of the relationship within Ohm's law. And so I can use resistance to check something like this. This is just a jumper cable that's part of this A-Tech set. Being that it's just a cable, it's just a wire, I expect to have very low resistance. And so if I hold this steady for a minute, we see we've only got 0.1 ohms of resistance, and that's a good measurement for a shorter piece of wire like that. We've also then got some different sets of resistors. So these are carbon film resistors. This first one should be within about 5%, or because that's a 10% band of 100 ohms. Here it measures 98.6. That's a pretty good measurement. I've got 1,000, and then I've got a 10,000 below that. And so here's a good example of where my auto ranging is going to take place on this meter. So I'm on a 1,000 ohm resistor. It should be within a percentage of 1,000, right? And so right now it's reading 994. And the important thing to think about here and pay attention to is that it has auto ranged. And so it says 0.994 k ohms, right? So it's reading 0.994 kilo ohms. The importance here is that depending on how I'm utilizing this information, I may need to make a conversion. So if I've got a specification in service information that says kilo ohms, great, I can compare that. If it is just in the native unit of an ohm, then I'm going to have to convert and move that decimal point 3 times to the right, which gives me 994. That's something that often trips up students, especially as we utilize Ohm's law early on. And so we want to pay attention to what are my units of measure right here. I don't want to mix and match kilo ohms and whole ohms. It gets to be confusing pretty fast. If we repeat that, this is a 10,000 ohm resistor. Give it a moment. Now it's showing 9.93 kilo ohms. So again, I've got to think about the kilo ohm factor and how that plays in. The last thing that I've got on here that's a good experiment to look at is a light bulb. A light bulb has a filament that has a certain amount of resistance, but that resistance value changes in a static form versus a dynamic form. So in the static form, this light bulb's only got 4.7 ohms. An important note to make about resistance measurements is that I cannot measure resistance anytime there's current flowing in a circuit. All the checks that we did, whether it was the wire or these resistors, was done with no current or volt drop present. When I try to hook up to something that has current present, I'm not going to get an active reading, right? So it shows OL, it shows this mega ohm reading sometimes. I can't do that because of the fundamentals with how this meter is going to measure resistance. Remember, it's got a power source and it's looking to apply a small amount of current and do some calculations. If there's current flowing in a circuit like this light bulb, where there's current coming from the power supply on my ATEC board, that current flow is going to interrupt and cause issues with how this meter wants to function. And so as soon as I take away the current coming from the board, I see a change. The other unique thing about light bulbs that I see happen is that I can see the role that heat plays when it comes to resistance. As heat goes up, resistance generally goes up. And so we saw what we had as a 4.7 ohm value previously. We went from about 14 and we continue to trickle down as this bulb cools off. Another function that we want to place in this idea of resistance and continuity testing is the audible continuity check on this meter. So this is pretty commonplace in most meters. This one is displayed with this small kind of audible icon that's also part of the diode button. I push that once and I get that little display up at the top. And what that does is give me an audible beep anytime there's continuity. So just like we talked about with auditing our leads for our meter, we can check for that audible confirmation. And then we can also do that with things like wires. So if I want to check the integrity of a wire from point A to point B, I can do that and get an audible beep. A lot of technicians find this useful in that we could have our meter in a place just close to us. We can do a check, we hear that beep, and we continue. And sometimes we're doing these checks underneath the dash. We're doing them in places where being able to see the screen and hold your hands in 2 points isn't always very easy. So great feature to have and to utilize. So next up, we're going to use this to measure voltage. There's several different voltage selections on this particular tool. And so the availability of these on your meter, if you've got a different meter, might vary. But in the basic form, I've got two readings of voltage. So I've got AC voltage, which is represented by that sine wave above the capital V. I've got DC voltage, which is represented by the dashes, which represents on off above that V. And then I've got a millivolt reading that is able to utilize both. It can be switched between AC and DC. So depending on what I want to measure, I'm going to make my selection here. I know that I'm using a 12-volt power supply within this board. It's DC. So I'm going to go to my DC setting here, and almost exclusively, with the exception of some hybrid technology, most systems on a car are going to be DC. And so we'll go to that DC setting, and you'll see some things come up on the screen. Right now we're getting a small number, and this is somewhat inherent to different meters. So whether or not they go to true zero or not, that's going to vary a little bit by the product we're using. These particular meters tend to hover around this 300 millivolt number. And so I can do a few things with that. One thing to point out currently on my screen, I get a confirmation of DC. I get that I'm in auto ranging. And so this number and where it's reading is going to change based on what I make a connection to. So right now it's in millivolts. If we go ahead and make a connection to our board, and so I've got one lead up here. We'll go ahead and switch these. We'll talk about the differences. If I got my red lead at the top, my black lead is at the bottom of the board, which is ground. I see that I've got 12.04 volts. And so the auto ranging took me from the millivolts where I didn't have a reading. It changed that for me and scaled it to the most appropriate point. And so then it reads a pretty nice clear number. Where I began to hook up and I switched the leads, but you see if I switch and I put my black lead at the power or the positive side, my red lead down at ground, I get the same number, but now I've got a negative symbol here that shows me the polarity has been switched. The important thing is, depending on the type of measurement I'm trying to conduct, that available voltage is still 12. And we don't concern ourselves too much with the negative or the polarity there. This is something that we want to pay attention to, but in terms of pursuing numbers, it's not an issue at the moment. So then let's talk about that range button. What does it do? So here again, it's kind of floating around. I push range once. Now I'm locked into millivolts. And so if I was to go try to repeat the same measurement, 12 is beyond the capability of that millivolt readout. And so I get an OL. And so that OL just means that the value I'm trying to read with the leads cannot be displayed on this scale. And so then if I push it again, I go to a volt port. If I take this away, we get a better representation of what it's trying to do. I take it away and I see now it's trying to show me a single digit and then all the way into the thousandth of a volt on this third spot here. So again, if I hook that up on 12 volts, 12 is not going to fit on that screen, and so I get an OL. I push it again. Now I've got two spots. Now I can read 12 volts. And so it's important to pay attention to where I push these buttons and what setting I'm in, and understand that maybe if I get an OL, it is just a setup error rather than something to be concerned with in terms of specs and actual readouts. The next thing we want to talk about with this is that the difference of measuring an available or open circuit voltage versus a voltage drop. So right now I'm just looking at open circuit voltage, and what that represents, say on a car, I measure across the positive and negative side of the battery terminals. That just tells me what is potentially there. It doesn't tell me exactly what's being utilized. To do a voltage drop test, I'm going to want to put my positive lead at the beginning of a load, an electrical load, and right after an electrical load. So just like this light bulb is. And so most times I'm going to get the same reading, but that is a more accurate depiction as to what this electrical load is using on its own. This type of testing is really useful in a lot of cases. Most of us would prefer to do volt drop testing like this over, say, resistance checks on a lot of components. The last thing that we're going to look at is how to measure current. And so on this one, I've got 4 settings. The two that are most applicable for us in automotive testing typically is just your amp setting and your milliamp setting. And so we're going to start with amps. Best advice is if you do not know what the load and current draw of a circuit is going to be that you're going to do the test on, you always want to start with the highest and then work your way back or work your way down to get a better or more detailed view of what that reading is. By starting with a higher amp value, we lower that risk that we're going to pop a fuse within this meter. Another thing that we could do is install a smaller inline fuse, not necessarily smaller value, but just a different packaged fuse that would be like an ATO blade style fuse in our leads. And then that would help save me the efforts of going through this. On this particular meter, the fuses are quite cheap, but if you're utilizing a meter like a Fluke, some of those fuses get to be quite expensive. So part of my setup, I went to amps here. Now I'm going to go move from the volt ohm port over to the capital A port. And again, this is rated at 10 amps. And so we know I've got some limitations on what I can measure. The important thing and distinction to make, and it's going to be difficult to see with the leads the way they are on here, is that in order for this tool to measure amperage, the current has to flow through the tool and the load that I want to measure. And so in order to make that type of connection, I'm going to have to be in series with this electrical load. And so that differs from the way that I make most other measurements. What we did previously for a volt drop was to measure before and after the load. That allows for the meter to be in parallel and really just reference what's happening with that circuit. If I was to do this connection whilst I'm set up in amps, this meter becomes a parallel circuit and that fuse becomes the load. So because there's no device in here to consume a load, doing this is like taking a piece of metal across these two components. On this particular board, the circuit breaker generally shuts off. Hopefully we save a fuse. Becomes a learning experience because I see that little light go out. On a car, imagine most of us have touched a wrench or something metal across a car battery, and it usually ends up trying to weld itself to the terminals. And so it might not be as dramatic, but if I was to do this here, I run the risk that my fuse inside is going to pop and become open, and then I have to replace it. The way to do this properly is to disrupt my circuit somehow. So I've really got to create an open point, and I've got to pay attention to, here's the point I was connected to, and then here was the connection. I'm going to take my leads and I'm going to reestablish the point I unplugged from and the component or wire that I unplugged. Once I do that, now the electrons have to go through this wire, through my load, through my meter, in here to be counted, back out, carried on to ground so that the circuit's complete, which is why the light's working. So I get this set up. This is in series. Now I see I've got 0.252 amps flowing through this. Because that is less than half an amp or 500 milliamps, if I wanted the better resolution, I could now switch down to milliamps, move my lead, plug it back in. I'm getting the same reading. I've just got some more resolution because I've moved down in my scale. So those are our three primary ways to utilize this meter, right? So we talked about how to do resistance checks and first verify that the integrity of my meter is in good shape. Go through measuring actual resistance. Remember, we've got to do that with the circuit off, no current flow. We talked about measuring for voltage, so open circuit or available voltage as well as voltage drops, and then also how to do current measurements and the importance to put the leads in series in order to make that connection.